I think we finished with kinematics and then we left just one topic, circular motion, right, sir? Uniform circular motion. Yeah. Yes, sir. So that we will leave, that's we will see later. So we will start with dynamics. Yeah. Okay. Yes. Yes, sir. We'll start with three dynamics. So first chapter. Yes, sir. So a little bit of background. What distinguishes dynamics from kinematics is kinematics we only worry about motion. So we don't like you could recall that always we say the ball is initial velocity this and then it's falling down. Okay, we never worried about what is the source of the energy or why this ball is moving, right? So if you worry about that, then we are talking about, yeah. If you worry about, then we are talking about dynamics. So what is the source? What is the force? What is the energy? Why it is moving? How it is moving? So in particular time, how it is moving, we are interested in kinematics. Why it is moving and what is the energy that we are interested. Like the topic covers covered by dynamics. Okay, that's the idea. Unlike kinematics, dynamics have the name you can see. It's dynamics. It's a variable. It will change as the source change. Everything will change. Yes. Okay, sir. Is it so? That's what we have dynamics and so study about energy of the material. What happens to energy? What is the source? Like what is the force acting? For to calculate clearly for constant acceleration, what happens to velocity, time, and displacement is kinematics. What happens to force, energy, and acceleration is dynamics. Okay, so maybe you can remember that we have wrote the equations saying that this is for constant acceleration, right? So here dynamics we talk about change of force. So also change of acceleration. So more than equations of motion, we have something. Yeah. Okay. Yes, sir. Now, yeah. So we'll start with Newton's law of motion and momentum. Okay. So there is a like um, bigger picture here, but that's a different story. Okay. Like Newton single-handedly invented entire thing. So he just had earlier observations, and he has to develop all the mathematics he require also. Okay. Sometime if we have time in future, we'll discuss those stories. Okay. Yes, sir. So now, so before talking about Newton's laws and then motions, first we will understand what is a mass. Okay. So far our elementary understanding of mass is it's just I think uh, s- amount of substance that amount of substance that occupied space. That's a definition that we used to have, right, sir? So that's maybe we can call it as a naive definition. Now here in dynamics, mass possesses a different character. So we call that character as inertia. Okay. Yeah, inertia. So so what is inertia is the resistance to change motion. Okay. Yeah. So it will exert some, like for example, if you want to push an object, okay, our finger also will receive partial force. Why? Because of inertia. No, resultant force we will study later. For example, let's say that I have this cap over here and this has mass. Now, uh, with respect to this notebook, this cap is stationary, right? It is not moving. So now I want to change its velocity. Now velocity is 0. Now I want to change its velocity. So unless until I apply a force, it will not move. The reason that unless until we apply a force, it's not moving is because of the inertia. Okay, so this works both for zero velocity, constant velocity as well. Let's say that it is going in constant velocity. Unless until I apply force, it will not change velocity. Okay, so this resist to change in motion is not only for velocity equal to zero, but also for some constant velocity. Okay, so this is a property of the mass. This resists the change in motion, inertia. Okay, inertia is a property of mass which resists change in motion, particularly velocity. Okay, sir. Now, you might have heard that there are three Newton laws are there. Okay. Yeah, first, second, and third. Eventually, all conveys the same information, but using different words and vocabulary. That's all. They all are same actually. Yeah. So, for example, we'll take. Yeah. So, okay. Before that, we have to establish one more idea. What is momentum? Okay. So, momentum is property of a moving object. Okay, so it's given by mass into velocity. So what is a mass multiplied by what is a velocity? So there's no clear cut definition for momentum. It's just a product of mass and velocity. Okay, it's just, but you can assure that it's a property of a moving object. Okay, now the idea we are going to get is change in momentum. Okay, so first we declare property of mass resists change in motion, right? Velocity. So what's the full definition? Unless until we apply external force, the velocity will not change, right? So that's the first law. That's law of inertia. So first law, what we are saying is, so first law. Okay, so no force, no change in velocity. Okay, this is first law. Now second law is like same, but if there is force, there is change in velocity. Can you see? I want. Okay, it's not. Yes, sir. Sorry. Mm. Yeah, is it clear, sir? Mm. Yeah. Okay. So first law says no force, no change in velocity. Second law says if there is force, there is change in velocity. Okay. Yes, yes, yes. Now change, for example, now one more question comes here. If there is force, let's say I have a two object, if there is force, will they change in velocity same rate? Do you understand? This question is very natural to ask. Yeah, so we get A and B, two objects. Let's say that I apply same force. Okay. Do they change? Let's say that both of them at zero initially, 0 meter per second. Will they change to same amount of velocity? This question naturally arises. Super. We already conveyed that the force are equal. Then it depends on the mass of the object. So this is not just change in velocity. This is somehow mass and change in velocity. So that's why we declare what is momentum here. So second law precisely says if there is change in momentum, then there is change in force. Sorry, there is force, not change in force. There is force. Second law. Yes. So change in momentum, okay, over time is force. So rate of change, force is directly proportional to rate of change of momentum. Okay. Now, what is momentum? Mass into velocity. So now we have declared it is change in momentum. Okay, wow. Yeah, so I'm going to write like P2 minus P1. Let's say this is final momentum, this is initial momentum. Okay, so change in time is a particular time period, so I'm going to take it T. Okay, so now P2 minus P1 is m v2 minus m v1. This is, we are taking one single object. Okay, initially it is going with velocity v1, and then you applied force, so it is after that it's going velocity with velocity v2. Okay, divided by t. So it's final minus initial. Is it clear, sir? So since it's the same object, their mass is going to be same, so I'm going to take out the mass v2 minus v1 divided by t. Okay, so what is this v2 minus v1 divided by t? What do you call this v2 minus v1? Change, this v2 minus v1 is change in speed. Change in velocity by time is nothing but acceleration. Okay, so but this is not the original derivation for super. Yeah, because we established that just applying force, this guarantee change in velocity, but by what amount it changes, the velocity change is guaranteed, is the product of mass. Yes, yes. Okay, so we understand, even if you apply same force for different material, whichever has the lower mass will be accelerated faster, whichever has the higher mass will be accelerating slower. Okay, so that's a Newton's second law. Now we can, for example, take it for granted. Let's say that 5 Newton forces apply to 2 kg mass, also 5 kg mass. Find the accelerations. So we know that F is ma, so A is F by m. So acceleration of first object will be 5 Newton force by 2 kg. So 2.5 meter per second square. So acceleration of second object will be 5 kg divided, 5 Newton divided by 5 kg. So 1 meter per second square. Okay, sir? Yes. Mm. Is it clear, sir? Yes. Now two laws are established clearly. So first law says, without a new force, without a force, not new force, without a force, the velocity will not change. That's first law. If there is force, velocity will change. That is second law. Okay. Now we come across one more problem. Let's say that I take a box and then I apply force in this direction. Also, I apply force in this direction. Let's say both direction I apply 5 Newton forces. So now second law says, if there is force, there will be change in velocity. Okay, wow. Now will change in velocity happen to this box? No. Why? Because it's equal. They are equal forces coming from opposite directions. Coming from opposite directions. So the resultant force is 0. So these laws work for only resultant force. Only if resultant force, some resultant force is there, changing velocity will be happening. Both first law and second law. Only if there is a resultant force, net resultant force is there. You can have multiple forces applying on the system, but the resultant force is 0 now. You will not have change in velocity. Only if there is a resultant force in some direction. Remember, in vectors we learn how to find resultant force. Okay, so using that, we have to find the resultant force. In that direction, change in velocity will happen. Okay, so the third law specifically says it's not only velocity can change, but direction also can change. Okay, now how to see or connect this first law to the third law is, we know the famous third law is force, every force will have equal and opposite forces. Okay, so let's say that Fa is equal to Fb, but how to understand and connect it with first law? Okay, so we'll see, for example, let's say that we are traveling in a bus. So the bus is actually going forward. Okay, this is our seat, we are sitting there, and all of a sudden the bus turns to the left. So what will happen to our head? Let's say it's bus is going very fast. We will go towards the right. Why this is happening is, our head has the inertia in this direction. Now we are not changing the velocity, but changing the direction. Since velocity is a vector, changing the direction also meaning that you are changing the velocity. So you will have a small force there. Its equal and opposite force will push you here, but the equal and opposite force is nothing but your inertia in the beginning. S- Now we are not moving, but we have mass, right? The mass inside the bus is moving. We have mass, so we have inertia. The bus, entire bus, the wheel has a grip, so that the bus turning here. Okay, let's say that when our head is here, but the head supposed to be here, right? In direct motion. So it has inertia only here. So the head want to go here. That's why we will tilt. But since the firmly attachment of the head with the body has more friction than this inertia, we'll just come back. We'll lean towards this position. Okay. Yes. 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 If it is a boat with no something to hold on, then you will fall into that side. Okay. Let's say that we are going in a high speed boat. So you don't have anything to. You just stand here, and all of a sudden you decide to turn this way. If you don't hold anything firmly, then we will fall here exactly in the place. Okay, so how to draw this? Let's say that this is a straight line. So we were going in the boat like this, standing. Okay, and the boat is turned this way, and we don't have anything to hold now. We will be going directly in this place, so we will fell down here exactly in the line where we were going. So that's where the inertia want to keep this person. Okay, to overcome this, we have to hold something firmly. That is what we call it as equivalent opposite force. Okay, so one way to understand, let's say that, have you seen that some boxes, no pull, only push? Have you seen this sign, sir? Okay, no pull, one only push. Okay, so this is because, let's say that this is a big cardboard box, and it has wheels or small something like, if we push this, okay, the cardboard also has to push us back. Okay, what will happen if the cardboard does not push us back? We will poke our hands inside the box. Okay, so equal and opposite forces. Only if the cardboard box push back, then the entire box will move from this direction. If the, let's say that the cardboard box is maybe wet or it's soaked in the rain, then it's like slightly soaked in the rain, then it cannot withstand our forces, so our hands will poke inside. So everywhere there is equal and opposite forces. Okay, even between molecules. Yeah, even um whatever the weight is, gravity pulling us down, right? The same amount we are pulling the earth up. But why earth is not moving in the direction? The mass is distributed Yeah, mass is distributed. Okay, if that is mass is more is the case. Okay, mass is more is the case because why if two-person fall down, one person is 100 kg, another person is 50 kg. Why both are accelerating same? Because the ratios of masses between the persons and the earth is huge. So it is always depend on the mass of the earth, not mass of the person. Yes, yes. The ratio is so small. That's why we are all accelerating equally. Yes, yes. If you take another, maybe no need to have equal, maybe one fourth of Earth or two fourth of the Earth, then it will make significant difference. Okay, actually, the solar system 99.9%, I think 9 or 8 to I'm not sure. Mass is in Sun. Okay, 0.28% is in Jupiter. So the not all the planets, the Sun and the Jupiter. It's the Jupiter is not orbiting the Sun. They both orbit about a common point, even for small fraction. Okay, but we will learn this in rotational motion only. Just a surprising fact. Okay. Yes. Yeah. So now third law says equal and opposite forces. For example, can you sit on a maybe okay, let's say if we stack multiple woolen bed sheets together, can we sit on firmly, or if there is a wooden block, can we sit on firmly? Which one we can sit on firmly? Wooden block. Why wooden block will give equal and opposite forces exactly by our weight. So this cannot give, so this will go like this. Okay, it will reach this point where its density has come enough close that it can give equal and opposite forces, then it will stay same. Okay, yes, until once it's compressed. Okay, we are sitting against a chair which can give equal and opposite force, we are sitting. We are sitting in a floor which gives equal and opposite force, we are there in the floor. If the floor no longer can give equal and opposite force, we will fall inside. Okay, sir, that's the logic. So all three laws are uh, they kind of like inertia, depend on inertia. Yeah. Okay. Yes. Now, so we learn about this F into ma, and what is very important is this force. Let's say that we are applying in some direction, so acceleration will be in the same direction. Okay. So force and acceleration will always in the same direction. Okay. So this is a perfect time to recall in the kinematics topics what we left. In the circular motion, okay, velocity of the object is in this direction. Force is always center, towards center. Okay. So acceleration is always towards center. It doesn't matter. In whatever the part of the circular motion, force is always towards the center. That's why we call it as a centripetal force. Okay. Yeah. Only the velocity and the acceleration is perpendicular. Okay. So in this case, tangential velocity will be this direction. If you go here, tangential velocity will be this direction. So how to understand this is, okay, forget this circle. Okay. Now let's say that you have a ball here. Now this ball is initially going in this direction. You apply one force here. Which direction it will go? Resultant force of these two, right? So this ball will go in this direction, right, sir? Now again, if you apply force here, the resultant direction will be this. Can you see the pattern, sir? So this depends on what is the system. In case of planets, gravity. Yep. Okay, sir. Can you see why it's always towards the center? So if you have constant force towards the center, you will always go in a circular path. Okay. So in case of planet, the massive star is there, and the planet will Actually, circle is the simplest case, elliptical is a normal case. So you will have force towards the center. Doesn't matter whichever the path, sorry, whichever part of the path you are, you will always have force towards center. In the case of, let's say that, so we decide to tie one rope and to the stone and swing it above our head. Now the force is provided by the tension in the wire. If there is no tension wire, let's say that you cut the wire, then the stone will go in this direction. Okay, sir. So in circular motion, acceleration is constant and it is towards the center always. So force is also towards center. Sorry, force is towards center, so acceleration is also towards center. Is it clear, sir? Yeah. Okay. So now we understand this Newton's laws. Um, in the bigger picture, momentum is very important. Okay. So we have two things called linear momentum and angular momentum. Fortunately, we don't have angular momentum in ASA level. It's very slightly irritating. Okay, for learners. Yeah. So what is linear momentum? So just mass into velocity. Okay. And here some learnings in the linear momentum. So for example, we already understand that if there is change in resultant force, there will be change in momentum. Okay. This change in momentum will happen over the time. Okay. So we already know that delta p by t, right? So F into t equal to delta p. So this quantity we call it as a impulse. Okay. Yes. So impulse has a unit of Newton seconds. So left side we have unit Newton second. So what right side we will have? Newton second. So momentum, whether it's change in momentum or momentum, will also have unit of Newton second. Okay. Can you check how it can have Newton second? So mass into velocity, right? So mass is kilogram, velocity is meter per second. So it's kilogram meter per second. Okay. Now if we take, maybe if we write F is change in momentum by change in time, right, sir? Okay. So it is equal to mass into acceleration. So mass into acceleration, yeah, mass into velocity by time. So kilogram into meter per second. Okay, sir. Can you see it? No. Yeah, I think it is right. Yeah, no. So this is right, sir. If you, what is the force unit, sir? Do you remember force unit? So force is Newton. Okay. Force is mass into acceleration. So it is actually kilogram into meter per second square. Okay, wow. So for change in momentum, I have force into time. So I have to multiply with time. So kilogram meter per second square into second. So I'll get kilogram meter per second. Okay, we are deriving from the same equation, but momentum has unit of Newton second. So what we can understand is, if you multiply Newton and second, you will get kilogram meter per second. Okay, that's the idea. So you should understand momentum has a unit of Newton second. Moment of force, however, has the unit of Newton meter. Yes. Okay. Energy also has a unit of Newton meter. Energy is force into distance. Yeah, work done is force into distance, right? So it also has the unit of Newton meter. Okay, just cross check. Okay. Yes. Now this linear momentum has some properties. First, okay. So there are, this momentum will come into equation only there is a force. Okay, if there is no force, yeah, for example, let's say that you have an object going in a constant velocity. Okay, it has mass m and then velocity v. It will have momentum of mv forever. Okay, it will have, yeah, some resistance is there. It will have mv forever. Okay, now let's say that we decide to apply some force. It doesn't matter whichever direction we apply, from this direction or this direction. Now there will be change in momentum. Okay, now how long it takes to happen this change in momentum depends on what is the magnitude of force you are applying. Okay, for example, we'll do one quick problem here. I have a mass of, sorry, object of 5 kg. Okay, now initially it is going with a velocity of 10 meter per second. Okay, now what force I should apply so that the object comes to rest in, let's say, maybe we'll take it easy, 10 seconds. So what was the question? Momentum, it has some momentum of 50 Newton second, right? So what force I have to apply so that the object comes to rest in 10 seconds? Okay, now how to construct? Now what type of force is this? Is it happening in the equal direction, sorry, same direction or opposite direction? So it will cause acceleration or deceleration. Hmm. So it will cause deceleration. So again we have to take, so by the way, momentum is a vector, sir. This I should have informed. Momentum is a vector. Whether it's linear or angular, it's a vector. Inertia is a scalar. Okay. Inertia is property of mass that resists to motion, change in motion. That's all. Okay. Is it clear, sir? No, they won't ask, sir. Not ASA level. Nobody dare to ask what is momentum, what is inertia, what is temperature, because nobody know. Okay. So you do not need to worry about that. Yeah, it's a scalar quantity. It's a scalar quantity, property associated with mass. If something doesn't have mass, it doesn't have inertia. That you can understand. Yes, yes. Okay. But same cannot be said for the momentum, because that's going to get pretty ugly in quantum mechanics. Even if it doesn't have mass, it has momentum. Uh, yeah, so far we'll just work with inertia. Okay. Yes. Okay. Yes, sir. So now what we are talking, initially it has momentum. And what is the question? How long it will take for the object to come stationary? Yes. So we can use this equation. Okay. Ft is mv minus mu. So I just extrapolate delta p is mv minus mu, right? Yeah. Now we can take the mass out. Ft is m into v minus u. Okay, t is here. We want only f. So f is m into v minus u divided by t. This is the equation. Okay. Now we have to take the directions. Okay, we want what is the force. So direction of force, we can take it as a positive. Let's say that this is positive direction. Then this direction only we have to apply force. Then only it will come to rest, right? Okay. Initially it has momentum 50. Sorry, velocity 10 meter per second. So we can take this as a negative. What is our final desired velocity? 0. Yes. So F equal to mass, which is 5 kg, into final velocity 0 minus initial velocity minus 10 divided by time 10 second. So 5 into 10 by 10. So 5 Newton force. So if you apply 5 Newton force, this object will come to rest in 10 seconds. Yes. Okay. Now we can flip this question. If I apply 10 Newton force, when If I apply 10 Newton force, how long it will take to come to rest? Can you figure out? Yeah. No, no. Yes. Half the force, half the time. Okay. Double the force, half the time. Okay. Uh, 1 minute, sir. Okay. Sir, impulse is a vector quantity. Yes, sir. Okay. Inertia is a scalar. Yeah, FT. Yeah. This depends on direction of the force. The direction of the force, whichever the direction of the force, impulse will have the direction. Yes. Okay, sir. So that's why we established sign here clearly. Yeah. Is it clear, sir? Yeah. Okay. So now, so people often confuse when to use impulse equation, when to use momentum equation. Is whenever there is change in velocity happens to one object and we are interested in the force provided by that object, then we have to use impulse. Okay, in one object. For example, ah, uh, uh, yeah, okay, okay. So okay, so however, I'll explain again soon when to use impulse, when to use. No, that's why most of the people stuck in momentum question. They won't able to figure out which equation to use where. Yeah. Okay. No problem. Now, so what we have to learn about collisions. So definition of collision is two object meet. Okay. Two objects meet. What is the one? What must be the one condition for the two object to meet? One, it can travel in opposite direction. Okay. Actually, you can. It can travel in same direction. Okay. For example, this goes in 2 meter per second. There is some object. It comes in 3 meter per second. Eventually, they will meet. Okay. So what is a mathematical condition is they should have a positive relative velocity of approach. Relative velocity of approach. Do you remember we discussed something called relative velocity going in equal direction and opposite? So two objects only if they have positive velocity of approach, meaning if they have the velocity that decreases over time, then they can collide. Relative velocity one with it. For example, in this case, the second guy is moving towards the first guy with 1 meter per second. So, sir, didn't we discuss relative velocity? No. No. Oh, okay, 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 sir. Okay, okay. So we will discuss relative velocity. Yeah. Now, what is relative velocity is, let's say that this is the ground. We are looking here. Okay. One train is going in this direction with 50 meter per second. Okay. Another train is going in this direction with 70 meter per second. This is train A and this is train B. Now, if you look from ground, this person will see train A is going in 50 meter per second. Train B is going in 70 meter per second. But a person in train A will see train B is going only in 20 meter per second. Because he is already going in 50 meter per second. Okay. Now, person in train B will see train A is going backward with 20 meter per second. Yeah. When one train overtakes, other train looks like, yeah, the train B overtakes. So train A, he will see the train A is going behind, right? Okay. So what is relative velocity is velocity between the body. So what do you mean by when you say train moves for 50 meter per second? It's with respect to you. When it is when you are in stationary position, it is easy. When both are moving, mm, yes. Yes, yes, yes. Mm. Okay. So if you are stationary, we just call it velocity. If you are moving, we call it relative velocity. Now, how to calculate relative? Okay. Maybe we have one more train C. Okay. This train is going in this direction 50 meter per second. Now, okay, sir, watch here. A, B, C, and this person. Who will see the fastest version of this train? Because he is going in this direction, this train is going in this direction. Yes. Okay. So with respect to C, this guy is going minus 50 meter per second, or in this direction, opposite, because we took this as positive, right? Okay. With A, this guy is going in 100 meter per second. He is going in 150 meter this direction. He is going in 50 meter this direction. Okay. 120 meter per second. Mm. Okay. So if two objects approach, okay, or the direction of velocities towards each other. Mathematical word is opposite, towards each other, right? Towards. Then you just add their velocities for relative velocity of approach. Okay. If they are towards, if they are moving away from each other, okay. If they are this is if they are moving in opposite direction. Yeah. So, or if you move away from each other also. Yeah, in opposite direction. This is in opposite direction. If it is in opposite direction, we are relative velocities. You just add both their velocities. Okay. In the case of B and C, we just add. In the case of A and C, we add. Okay. If they are in same direction, then you subtract from the highest to lowest. Mod. Yes. Okay. If one person is going 50 meter this direction, other person will, the train person in C will see B going in this direction 120 meter per second. Okay. So this is what we call it as relative velocity of approach, relative velocity of moving away. Okay. So what we learn from here, if they move in same direction, relative velocity will be difference in their velocities. Okay. If they are moving opposite directions, it can be towards or away. Then the velocity sum of their velocities. Is it clear, sir? So that's how we have to find relative velocity. Yeah, only two. And let's say that train A is moving is 50 meter per second. Train D is moving is 50 meter per second. The relative velocity is zero. Yeah, stationary. Maybe from the ground we can see both of them are traveling in 50 meter per second, but to each other they will be moving with zero velocity. So this is what we call it as relative velocity of approach and relative velocity of receding. Yes, please. Hmm. This person moves backward in 50 meter per second. Yeah, that's it. That's it. Okay. Maybe if the person is jogging very fast with 50 meter per second, then they will see this person is jogging with 100 meter per second. Yeah. Yes, 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 yes. If he can, like Endran movie, if he can run like 50 meter per second, then they will see this person is just running, but maybe running on a treadmill. Yes. Okay. So this is what we call it as relative velocity. So what's the takeaway here? If both objects have velocity in the same direction, the difference in the velocity is relative velocity between them. Yeah, added. No difference in velocity if same direction. Okay. Then if they are in opposite direction, then we add their velocities. So this is relative velocity. Okay. Now two objects can collide only if they have positive relative velocity, meaning that they are moving towards each other, or one is going slower, or if they both are going in the same direction, one is going slower, another one is going faster. And now let's say that here is a box A and here is box B. Okay. Now box B is moving with 10 meter per second in this direction. Box A is moving with 5 meter per second in this direction. Do you think they are going to collide, sir? Okay. So only if they have positive, meaning that in the direction they should have the velocity. Only if A can catch up B, it can collide, right? That's what we try to say. It should have a positive mm. Okay, sir. Yes, yes. Okay. In other words, with respect to A, sorry, with respect to B, you should catch up. You should have higher relative velocity in this direction. Okay. Now, if you are in B, you should look A. A is approaching you with some velocity. It can be 1 meter per second or 2 meter per second. But it should approach you with some velocity. If it is slowing down or it is receding, then you are never going to collide, right? Hmm. Hmm. Yes. Hmm. So okay. Nope. So you have to watch. You have to read the question carefully. They will say when the A will overtake B, meaning that A is running in a separate track, B is running in the separate track. So that is purely kinematics question, not dynamics question. So there you will use equations of motion. Okay. Yes, sir. Is this clear? Okay. Now what is collision is when two objects meet. So we establish when two objects can meet only if they have velocity, if they going in opposite direction or if they have a reasonable velocity of approach. Yeah. Okay. Now, yeah, sure. Yes. Yes, sir. Okay. Yes. Now, so what do we mean by collisions? Okay. So mean that they collide, and there are two type of collisions. Okay. So one is elastic. Yeah. Yes, sir. Elastic and inelastic. Okay. So we know that elastic means that it's a perfect recovery. So elastic means no deformation to the object. They are perfectly rigid bodies. So when two objects collide, the force exchange rate, this happens 100% to the velocities. Yeah. No, not all the forces applied. All the exchange force, right? All the exchange in force. One object will extend force on other object. This happen in 100% only in velocity. Okay. Then this is a elastic collision. In inelastic collision, it's not 100%. Never 100%. Maybe 5% you hear a big sound, bam, or the body, one of the body deformed, broken. So some of the energy is utilized there. Okay, so it's not 100% use in velocity. In other energy resources also, the energy, the force convert, the force used to maybe just to break down the object instead of slowing down. Okay, so, do you understand, sir? So here deformation, also you will get light, sound, whatever the energy went other than changing the velocity. This is etc, not limited to. Okay, yes, so it can be change of shape. Yes, yes. If let's say two trains are colliding and both the trains engines are completely done, meaning that they are shattered. So yeah, the force is utilized to deform the iron or metal, right? Yes. If engine is so rigid, all the passengers are cooked passengers. Okay, that's why they put the engine, actually, not because it's actually it is a good idea to put the engine in the back because it's expensive than all the other coaches, but lives of the passengers are more expensive than the engine, so it kind of act as a shock absorber. Okay, so we will learn the what is bumper and what is the use of bumper. Yes, sir. Okay, yeah. So in both the cases, momentum is conserved. Okay, momentum is conserved. So this word is very important, conserved. Both cases. Yes, super. Can you see? Okay, so 1 minute. I'll explain what is conserve, sir. Meaning that total initial momentum is equal to total final momentum in both the cases. So conservation of momentum. So it doesn't matter what. Yeah, conservation means in any given point, if you take the total momentum, it will be equal. Okay, so total initial momentum must be equal to total final momentum. Let's say that initially two objects are in this direction. Okay, they have some other let's say this has mass and velocity, and this has m1 and v1. Maybe uh, yeah, maybe I'll put it in equation. Okay, let's say that this is object A and this is object B. Okay, we'll take two objects A and B. Mass of the object is ma, mass of the object B is mb. Okay, now initial velocity of the object is ua. Initial velocity of object B is ub. Final velocity of object is va. Final velocity of object is vb. So total initial momentum ma ua. This is momentum of this, right? Plus total initial momentum of this guy mb ub is equal to final momentum. So ma va plus mb vb. Okay. So this equation right there, we have to see the different forms of this equation. This is how most of the problems will be solved in momentum. Okay, so ma ua plus mb ub is total initial momentum. Initially, it has a momentum of mv ub. This has the initial momentum of ma ua. After that, it has the final momentum of ma va. This has the final momentum of mb vb. Yes. So what is the total momentum before the collision? That's exactly what is the total momentum after the collision. Okay. Why mass is involved here is, let's say that during inelastic collision, some piece of the mass is ejected or torn apart. The rest of the mass will have velocity, right? The torn mass also will have a velocity. So if you add all together, they will have the total initial momentum. Yeah. Yes. No. Even if the missing pieces, they will have velocity, right? If you calculate their mass and velocity, then you get total momentum conserved. You will see the total momentum is never, it didn't change. Okay. But kinetic energy, however, since it's not 100% converted to kinetic energy, elastic collision, kinetic energy is conserved. In inelastic collision, you cannot say kinetic energy is not conserved. Because the velocity of the object is going to change, right? Yes. Okay. Is it clear, sir? This equation we have to. Okay. Is this clear, sir? Can we move to next page? Yeah. Okay. So now we will take this equation. So let's say that I have object A and object B. So we established MA UA plus MB UB is equal to MA VA plus MB VB. Okay. Wow. We have to write in multiple ways so that we can make most out of this equation. Now let's bring sir, by the way, we have assumed all the directions are this side. VA is in this direction, UA is also in this direction, VB is in this direction, UB is also in this direction. But if direction changes, that we have to accommodate the change in sign also. Yes, minus. So this depends on our calculation. So we can take anything positive and then we can do all the opposite things are negative. Okay. Yeah. So now maybe I'm going to rearrange this equation in this way. So MB VB. Sorry. Yeah. So how I want to rewrite this equation is MA VA minus MA UA is equal to MB VB minus MB UB. Can you see what I have done, sir? So I have brought this guy here, so he become minus. Okay, and I no, one should have plus. So if I move here, he will have minus. Okay. Yes, sir. Can you see? Yeah. Now, so I'm going to write this as MB UB minus MB VB. Okay, wow. Yeah. Now, if you take masses are common, so if you take out VA minus VB, sorry, VA minus UA. Okay, is equal to here also you can take. I'll take minus mass common. So you will get VB minus UB. Can you see how that works? Okay. Yes. Now they would have met for some time, right, sir? So the collision, yeah, the collision would have appeared for. So most of the cases we take it as instantaneous. Okay. And why it's not here the part? Whatever the time A met B is the same time B met A, right? So it's equal. So if they are in the denominator, we would have cancelled out. Yeah, that's why it's not here. Okay. Now if we multiply it by time both side, sorry, divide by time both side, then we will get clearly MA VA minus UA VA minus UA divided by T equal to MB VB minus. Okay, wow. VB minus UB by T. What is this? Okay, in other words, force exerted on A to B is equal to minus force exerted on B to A. Newton's third law. This VA minus UA by T is acceleration on A, right? This VB minus UB by T is acceleration on B, and there is a minus. What is mass into acceleration? Force, right, sir? So force exerted on this guy from this guy, right? This is what we are learning. So that's why I wrote it as, maybe I can write it as BA. So I'll write it here. So FBA is equal to minus FAB. Okay. Can you see Newton third law pop out of nowhere? Okay. So, mm, yes, yes, but single object, you have to act on some other object. Then only you will have equal and opposite force. You understand, sir? If you punch in air, if you punch in air, let's assume air resistance is also not there. You didn't do any useful work. Only if you punch against a wall, then you have done some useful work. Yeah. Okay. Yes. Okay, sir. Yeah. So we can use multiple forms. You can use this form, or you can use this m into v2 minus u2 is equal to m into v1 minus u1. Here is a minus. Okay. Now, if both are same, let's say that both are same masses. Okay. So A and B have same masses. Then what will happen to these masses? So they will cancel out. Ma into Va minus Ua is equal to minus Mb into Vb minus Ub, right? So masses will cancel out. So what this is, Va minus Ua is equal to minus Vb plus Ub. I have brought the minus into inside. Okay, sir. So now Va minus Ua is equal to Ub minus Vb. Okay, sir. Now I want to bring U same side. Okay. So Ub plus Ua is equal to Va plus Vb. What is this? What we are doing to the velocities? We are adding. In relative velocity, what case we will add? Yes. So if two same masses traveling in opposite direction, they will just exchange their velocities. Okay. Yeah. We clearly have. Yes. Ah, yes. Mm, mm. So let's say that here is mass, same mass. Okay. This is traveling in 5 meter per second, and this is traveling in 3 meter per second. And once they collide, after that, this will travel in 5 meter per second. This will travel in 3 meter per second, because their relative velocity of approach is equal to their relative velocity of separation. Okay. But why their velocities are changed? Because they have same mass, right? Yeah, elastic collision, no deformation or something. Okay. Now, to answer your question, they have same mass, but why they exchange velocity? That's your question, right, sir? Despite of they have same mass, who has higher momentum? One with a higher velocity. So he will eject back with a lower velocity. He will lose velocity, he will gain velocity. How much he lost is exactly how much he has gained. So that's why exchange of velocity. Is it clear, sir? Yes. Yes. Mm. Yes. Yes. Okay. So we do not need to remember the entire derivation. We just have to remember this equation, remember this equation, and remember this equation, and remember this equation. So any momentum formula you can address, momentum problem. I think so far you would have solved problems, but you didn't know the theory behind it, right, sir? Yeah. Okay. Okay. Yeah, you can have any notion you want. Mm. As long as yeah, yeah. As long as we are in clear with the directions of the objects, we can use any formula we want. Yes, yes, sir. Okay. So, this is it. We have learned three things. Okay. So first we learn conservation of momentum, and then we learn um, in both elastic collisions and inelastic collision, momentum is conserved, but kinetic energy is not conserved. Okay. In elastic collision, total kinetic energy is conserved because of that. Okay. Now this is one of the derivation because of the conservation of energy. Okay. Relative velocity of approach is equal to the relative velocity of separation. Okay. So 1 minute, I will check one more sub case if it is true for all mass or yeah. Okay, sir. Now, so now we took relative velocity of approach is equal to relative velocity of separation, right? This is true for all the cases, whether their masses are equal or not. Okay. Because if they, the simplest case is if their masses are equal, they will just exchange velocity. Yeah. Yes. In simple cases, if their masses are equal, they will just exchange the velocity. Otherwise, whatever the momentum this has decreased, by the same amount of momentum, this would have increased. So even if they have ratios of mass, even if they have different masses, it will work. Yeah. Okay, sir. Yeah. And remember, this works only for perfectly elastic collision, not in inelastic collision. This relative velocity of approach is equal to relative velocity of separation only for elastic collision. Mm. Yes, sir. Is it clear? Yeah. Super. Okay. So we have only one more thing to explain, then we will solve problem. Uh, I think should we do some problem with momentum? Yeah. Okay. Sir, if it happens in a straight line, it's a linear momentum, sir. That's all. Ah, okay. We have to discuss about that also. So momentum is a vector. You can actually resolute vectors, right? Okay. We'll solve those problems. When we solve the problem, we'll explain. Okay. So linear momentum in straight lines, sir. That's all. Angular momentum is circular motion. By the way, momentum is a vector, sir. Yeah, yeah. Hmm. Okay. First, we'll do a simple problem. Oh, no simple problem in momentum. Nice. Okay. Yes, sir. So we'll do this question. This is a 12th question in. Uh, okay, 12th question is in this one. S15 QP13. 12th question. Okay, sir. Yeah. So now there are two balls X and Y. Okay. Now X is moving with 5 meter per second. Y is moving with 15 meter per second. Okay. They take a perfectly elastic head-on collision, and ball Y moves to the right with a speed of 7 meter per second. Okay. What is the speed and direction of ball X after the collision? This is a question. Okay, sir. So, um, do you understand the question, sir? Hello. Hi, sir. Do you understand the question? Oh, okay. 1 minute, sir. Can you hear me now? 1 minute. Oh, I see. Okay, 1 minute, sir. Can you hear me now, sir? Yeah. Oh, sorry, sir. So this is a question from this paper. S15QP13. Okay. So 9702 S15QP13, question number 12. This question. So now we have two balls X and Y. X is moving to the right with 5 meter per second. Y is moving to the left with 15 meter per second. Okay. It's a perfect elastic collision. After that collision, Y moves with 7 meter per second to the right. What is the velocity of X? This is a question. 1 minute, I'll share the question so that you can see. Yeah, perfectly elastic collision. Can you see the question here, sir? Yeah. So 1 minute, sir. Can you see the question, sir? To the left or the right? Sir, that's why we should not make mistake. Only if their masses are equal, they will just exchange velocities, right? Can you see they are clearly not equal because this has 7 meter per second going to the right. So how do you work this problem? What concept or statement you will take to start with? First see the question, sir, and tell me if you understand. Yes. Mm. Sir, this M3 and V3 were because they are not coming as a single object finally. Okay, wow. So they are, yeah, no, we don't care. Remember in the question, mass is not given. So mass is not given. No information about the mass is there, right? So out of four velocities, three velocities are given. Fourth velocity we have to find. So what we have to do, we have to use the concept of relative velocity of approach is equal to relative velocity of separation. Okay, do you understand, sir? Because masses are not involved. Remember, we discussed here relative velocity of approach is equal to relative velocity of separation. Okay, and they are traveling in opposite direction or same direction? Opposite direction, yes. Okay, so this will work. This works perfectly. So we'll see. So UB plus UA is equal to VA plus VB. This is what we are at it. Okay. Yeah. So now, so it's X and Y. Okay, sir. Maybe to avoid the confusion, I'll write like this. Okay. So UX plus, sorry, UY plus UX is equal to VX plus VY. Okay. I think, yeah, B is Y and A is X. That's how I wrote. Yeah. Okay. So now ux is 5 meter per second. We'll take this as positive, or to the right is positive. Okay, if it goes towards the right, it's positive, and uy is minus 15 meter per second because it's left. Okay, so vy is 7 meter per second. Now we have to find vx. Okay, from here, so we know that vx is uy plus ux minus vy. So uy is minus 15 plus ux is plus 5 minus vy is 7, just plus 7. So we'll get minus 50, so minus 10 minus 17. Now please tell me where where we went wrong, sir. Minus 15 is there. Yeah, ux is it towards right is positive? Yes. Okay. Ah, sir. Yeah. Now this is in this direction, so this would be plus only. But this is in minus. Minus vy. I don't know. Okay, 1 minute. Ah, 15 should be in plus. Okay, so we'll forget about this. We'll see relative velocity of approach. What is relative velocity of approach? It's 5 plus 15. So it's 20 meter per second. So this should be equal to relative velocity of separation, right? So one is going in 7 plus x is 20. So x should be 20 minus 7. So 13 meter per second. Okay. So since this we derived from same masses, it's not working here. Yeah. Okay. So now 13 meter per second. Now we have to work. So actually, it has positive, negative. We have to involve. But since we work logically, you see, now this one is coming from 15. So this is 5. After that, this goes in 17. So how much it has decreased must be converted to this direction. Okay. So it should have moved in this direction with 30 meter per second. Okay. Yeah. So 13 meter to the left. Yes. B. Okay. Yes, sir. But sometime we should not quickly jump, because sometime we have to work the direction like in opposite direction, and that this direction is very important in momentum. Yes. Okay. Super. So it is 13 meter per second to the left. Okay. Yes, sir. Yeah. So actually, this is easy. Relative velocity of approaches, relative velocity of separation. Yes. Okay. So we'll see if we can do some other question. Another 12th question. Yeah. So this question is again 12th. See, momentum question is 12th question, sir. Yeah. 9702 W15 QP 13. D. 1 minute, sir. Yeah. Okay. Yes. So We just have to work on this relative velocity of approach is relative velocity of separation. Okay. Yes, sir. Yes. Whether so first thing we should see whether if mass involved or not. Second thing we should see whether they are going in same direction or not. Okay. So if it whatever the decrease in kinetic energy of this object, thus that plus all the velocities involved, the total energy is same. Let's say that initially it has 50 joule. Okay, and this initially has 30 joule of kinetic energy. They collide. After that, this has 40 joule and this has only 20 joule. How much joule is missing? 20 joules is missing. This remaining 20 joule went to kinetic energy, some loss. Okay. Now, if you have this velocity and this velocity, you can find how much is missed. That subtract from the, you take this velocity and you know the mass. So, you can find the final velocity, half mv square. That's it. Oh, yes, half mv square. So, you know the mass. So, you will know the final velocity. Yes. Hmm. Okay. Yes. So, let's say that I have an object of 50 joule, it has kinetic energy, and then it has collided with something. After that, it has energy of 40 joule. Now they can ask for what is the final velocity. Simply you can equate this to half mv square. Whatever the v you are getting is final velocity. Yes. Kinetic energy is half mv square, right? No. 10 we do not. 10 is lost to the surrounding. What is the remaining? That's only you. Uh, yes, sir. Yes. Mm. Okay, sir. Yes. Um, okay, so these are relative velocity of approach is equal to relative velocity of separation questions. Now, if you have, if you want to have a little more fun, then we should took final velocity. They don't have direct momentum question. Okay. So you can see question 11, sir. This one. So this is 11th question in 9702. 1 minute, sir, 1 minute. Yes, 13, QP 11. Yeah. Yeah, 11th question. Yes. Mm. Okay. What method? How we were proceeding, sir? Now this is definitely inelastic collision. Mm. Mm. Yes. Mm. Mm. Yeah. What? Mm. The problem with this method is we don't have the information of final velocity, right? Yeah. And also, sir, kinetic energy of object B is zero because it is in rest. Okay. So how to solve this? First, find the final velocity. Okay. So now the problem is this. So you have a object of 2 kg moving with 3 meter per second. Okay. And you have another 1 kg object moving with zero rest. Okay. Now they are colliding and it's an inelastic collision. The masses stick together on impact. Okay. Question is how much kinetic energy is lost on impact, right? Yeah. Now, first we'll find what is the final velocity. We can use this equation. Um, so m1 u1 plus m2 u2 is equal to m1 v1 plus sorry, m2 v2. Right, sir? Okay. And in this case, v1 and v2 are same, right? Yeah, tell me why they are same. Think. Because the masses stick together on impact, right, sir? So finally, they should have the same velocity. Then only they can stick together. Mm. So m1 u1 plus m2 u2 is equal to m1 plus m2 into v. Okay, can you see that I took v1 and v2, I wrote it as v. Okay, now v will be m1 u1 plus m2 u2 divided by m1 plus m2. So it will be 2 into 3 plus m2 1 into 0 divided by 2 plus 1. Yeah, but momentum is conserved in all cases, right, sir? First, we want the final velocity of the system. Then only the question is how much energy, how much kinetic energy is lost on impact, right, sir? Mm. So, so it will be 6 plus 0 divided by 3. So 6 by 3. So 2 meter per second. So finally, they are moving. Both of them they are moving towards sorry 2 meter per second because they stick together and both of them they are moving 2 meter per second, right? So now let's calculate the initial kinetic energy of this guy. So half into 2 into v square is 9, 3 square. So it's 9 joule. This guy initially have kinetic energy of 9 joule. This guy initially have kinetic energy of 0 joule. Okay. Finally, the total mass of the system is 2 plus 1, 3. Ah, yeah. Okay. Now, final velocity is 2. Okay. So the total kinetic energy of the system is half into mass 3 into velocity. Their velocity is 2. So 2 square. So 3 into 2, 6 joule. Right? So, yeah. So what is the difference in kinetic energy? So 9 minus 6. So 3 joule. So option D. Yes. So this type of question, first we should find the final velocity. Then we should calculate the final kinetic energy. Then we can see what is the difference between initial kinetic energy and final kinetic energy. That kinetic energy is lost in the impact. This one is no final collision. 3 is mass, both objects together. 2 plus 1. Ah, yes. Is it clear, sir? Yes. Okay. So we'll see one more. Now, only one more small topic to complete this chapter, sir. Yeah. Then next class we will solve problems in these three chapters. Yeah, yeah. Okay. Now try this question, sir. Question 13. Okay, so this is question 13 in 1 minute, sir. 9702 W13 QP 13. Yes. Yes, sir. Super. Okay. So can you see it's the same question as the earlier questions? Yes. Mm. Yes. Yes, sir. Yes. Super. That's all you have to learn in the momentum and kinetic energy. Okay. So actually, if both masses are given, question is much easy. So you just substitute their values exactly, and then we proceed with this. This type of questions are understanding. Okay. So what's the method is we write the formula and we write the equation. We rewrite the equation up to our desire. That's all. Okay. Yes, sir. Okay. So we'll do more questions later. Now we will do with the last session. Okay. So that is 3.2 non uniform motion. Okay. So this non uniform motion is wherever the force changes, as a result, acceleration changes. For example, if there is a mass m, okay, if it is if it is given a constant force, it will have a constant acceleration, right? Okay, but let's say that over the time force is decreasing or increasing, then the acceleration also will decrease or increase, right, sir? Yes. Okay, so this is what we call it as a non-uniform. By the way, sir, in momentum we didn't solve. Actually, momentum is a vector, right? So if two objects collide and one object goes in this direction, other goes in this direction, we have to worry about horizontal. Yes, horizontal and vertical momentum. Horizontal momentum is conserved, vertical momentum is conserved. But however, we'll solve this type of problems together. Okay, so that's why I didn't attend here. Yes, yes, yes. This is very important. This is where. Mm, mm, mm. Have you played carom board, sir? No, no. Imagine, imagine. Just imagine. Okay, if the striker is the coin is here, striker exactly hit here. Both of them will go in the same direction. But if the coin is here and striker hit here, s- that's the momentum problem. It's a head-on collision. What do you mean by head-on collision is both have same. What is the velocity in that same direction? That's when. So remember, it's a vector. You can move it here. Okay. So no, no, we will address this. Don't worry. See, the idea is, let's say this coin has a velocity in this direction. If you place this coin, will the velocity is going to change? No, that's all. Why? Because velocity is a vector. These two are coplanar vectors. It's not going to change. Okay, sir. Yes. Uh, yeah. Okay. So, however, this type of questions are very important. So, we will solve it in the problem solving session. Okay. So, I didn't take it here because itself will take like 5 to 10 minutes. Okay. So, but definitely we will solve this problem. Okay. Yes, sir. Okay. So, now what we are discussing in a non uniform motion, forces changes, acceleration changes. Tell me what in real life, what are the situations that this occurs, sir? Change in force happens. Super. Any friction or air resistance, yeah, any frictional force, any friction force. Air resistance is friction due to air molecules. Okay, if you put something in the liquid, the viscous force that is due to friction between the liquid molecules. Drag. Okay, so all this depends on square of the velocity. Yeah, this force directly proportional to square, whether it's upthrust or air resistance. The drag is proportional to square of the velocity. Okay, we do not need to worry about this. It's proportional to. Okay. Now, but there are formulas using this. That formulas we will learn in forces, density, and pressure. Okay. But I'm going to give you a heads up. For example, let's say that so there are two type of forces actually. Okay, and this based on the energy. Okay, so you can take conservative and conserve and non-conservative. Okay, for example, here's Earth. Okay, at this point, let's say that you have 0 joule potential energy. You go to 10 meter, then you have 100 joules of potential energy. What is the formula potential energy? Change in potential energy is mg delta h, right? Hmm. Now, does it matter how you go to this position? Because what we are calculating is only difference in height. So it is independent of path. This work done is independent of path. So this is conservative. If work done is independent of path, okay, the field is conservative field. The force is conservative force. Okay. Hmm. Now let's say that we are swimming inside a swimming pool. Okay. We start here, we went there and come back. We came to same position, right? So theoretically work done should be 0. But is it? Because we have to swim across the drag. So this is a non-conservative force. So the non-conservative force depends on the path length. It doesn't matter which direction you are going. Whichever direction you are moving, it will show some force in the opposite direction. Okay. Very good examples are air resistance, in friction, drag. They are non-conservative force. Okay. So it doesn't matter from where to where. We don't care. How long you are in the system, that time you will drain energy. That's all. Yes, sir. So this non-uniform motion mainly because of this non-conservative forces such as friction, drag, air resistance, mechanical friction. Okay. What happen is over the time it will keep on increasing. Okay. So one good, very good example is terminal velocity and free fall. Okay. So now what happens is, let's say that no air resistance. Okay. So if we drop the ball initially at 0 meter per second, for every second, in first second, its velocity will be 10 meter per second. In second, it will be 20 meter per second. Third second, it will be 30 meter per second. Why? Because acceleration due to gravity is 10 meter per second square. Each second, its velocity will keep on increasing if there is no air resistance. Okay, the velocity keep on increasing, right? Let's say that you are doing 100 second. Okay, your velocity would have increased by 1000 meter per second. Okay, yes, without air resistance. But problem is there is air resistance. So what this air resistance does and how this air resistance depends is, as we said, it's proportional to square of the velocity, but we do not need to worry about that. That's out of scope of the syllabus. Okay. Now what will happen? As your speed increase, it will have more force opposing. Okay. So after some yes. Okay. This doesn't depend on how long you are in air. No. How fast you are moving. The faster you move, I will provide more opposing force. Okay. So first of all, why this object is falling? Gravity or weight of the object. Okay. So eventually, I'll call it upthrust. Air resistance, I call it upthrust. So eventually, the weight will be equal to upthrust. So what happens to net resultant force? 0. So not net resultant force is 0. So whatever the last velocity, when the weight becomes weight, the upthrust equal to weight, the ball will keep on falling down with the same velocity. That velocity, what we call it as a terminal velocity. Weight, weight. Mm. Yes. Yeah, it is in equilibrium. Remember the condition for equilibrium. It's in constant velocity. Yes. Okay. Yes, it will be in the same speed. Yes, terminal velocity. So what happens is initially you drop the ball. Now its velocity is 0 meter per second. So no upthrust is acting. It will keep on falling. At some time, let's say that its velocity is, let's say, 100 meter per second. Okay. Now, as it reaches from 0 to 100 meter per second, now upthrust is 0. But when you reach here, upthrust will be significant amount because it's proportional to square of the velocity. Okay. Eventually, the upthrust will be equal to the weight. So in maybe let's say that at that time you are moving at 150 meter per second. So for rest of your falling, you will just go with 150 meter per second. That's what we call it as a terminal velocity. Okay. So when it can change, maybe let's say that you in the meter you try to expand like a parachute, open a parachute, then this terminal velocity will again decrease. Yes, sir. Is it clear? Yeah. So same goes with liquid. If you are going down the liquid, okay, but liquid upthrust is rho GH. Sorry, rho GV. Pressure is rho GV. Upthrust is rho GH only. Yeah. Okay. So, but we have the derivation for this that we will see later. No, I mean it's a easy derivation only. Yeah, yeah. It's a easy derivation only, but we'll do it later. Okay. Now, whenever we address these type of problems, where most of the people make mistake is they will just take the force. We should not take the force. We should take the resultant force. Okay. Remember when we solved this problem 9702 S25 QP. What's the problem? Yeah. No, not today. So QP 11 la sure, sure, please. Yeah. Yes, sir. I forgot the question. I'll tell you later. Yes. No. So remember that we failed to account for weight and then we got some other answer, different answer, resultant force. Object was falling down with 50 meter per second and some force was applied for 2 seconds. What is the final velocity? Remember the first class we solved question like this. Yeah, yeah. Okay, okay, no problem. So, but yeah. So if we don't account the weight of the object, then we arrive at wrong some other answer. Resultant force, not yeah, not the whatever the force we want to consider. What's the resultant force? Yes, 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 yes. But um, uh, I think apart from momentum, they don't ask really different direction of forces and things in ASA level. But I don't know why. Only in momentum they give directions, momentum and velocity, theta. Yeah. Okay. So so these are the things that we have to learn, sir. This is 3.2 non-uniform motion. But in 3.2, we will understand this drag and upthrust very detailedly in the fourth chapter. Yeah. So how upthrust is working and how to derive it. Okay. Yeah. So with that, dynamics is done. Okay. S- yes, sir. So Saturday, if you are free, we can solve questions in this three chapter. Okay. So maybe I'll pick difficult questions so that we can solve. Yeah. So is it clear, sir? No, no, that we will solve during the problem. Yeah. I'll pick questions that involve such questions. Okay. Yeah, yeah. Yes, sir. Sure, sure. That's momentum. Okay. So you want the theory behind it, sir? That question? Okay. Okay. Maybe let's do it now. No problem. Okay. Let's say that object A is going in this direction with the initial velocity of UA. Okay. So object B is in this direction with initial velocity of UB, and they collide. As a result, one goes up and another one goes down. Okay, let's say that this goes with velocity v. Yeah, it can happen in any degree. Okay, it's not restricted. Depends on the orientation of the object. Okay, let's say that you take object A is like this and object B is like this. If object A hit object B, which direction object B will go? Yeah, so this depends on orientation of the object. Okay, it need not to be uh, how it if it have head-on collision, it can go different direction. This depends on like carom example. This depends on where it hit. Okay. Yes. Okay, sir. Now, uh, this VA and VB, we are interested in VA and VB. Why? Because we know that if you just take, okay. Now let's take object B, sorry, object A. Its final velocity VA, right? And some theta is given. Now this VA we can actually take into horizontal and vertical momentum or horizontal to vertical velocity. So its horizontal velocity will be VA cos theta and vertical velocity will be VA sin theta. Okay, wow. Sim okay. So because maybe draw here, now it is opposite. So it is VA sin theta. It is adjacent, so it's VA cos theta. VA is a hypotenuse. Can you see why, sir? Yeah, okay. Now if you take object B, now again, now this goes with some angle theta. So its vertical component will be VB sin theta. Horizontal component will be VB cos theta. Okay, wow. Now what's the momentum is, we discuss about linear momentum. Yes, sir. So initially both objects momentum only in horizontal direction. Do they have momentum in vertical direction? No. So total momentum in horizontal direction before is equal to total momentum horizontal direction after. Yeah, it is moving. Some part of this is moving in horizontal direction, right? That's why momentum is a vector. Some part is moving in horizontal, some part is moving in vertical. Resultant only you are going in this direction. Yeah, okay. So now, I think once we form the equation, you will understand. So see this here. So MAUA plus MBUB. This is what is this? Total momentum before collision. Okay, is equal to, so MA VA sin, cos theta plus MB VB cos theta. Please tell me what we are trying to do here. Because cos theta is a horizontal component. In that direction, Okay. Now, this is for horizontal. What was the total momentum vertical before? Nope. Is it same? No. What is the total momentum vertical initially? Vertical. Initial, sir. Initial. Here, do they have any vertical motion initially? No. So 0 is equal to VA sin theta. That's all. Okay. So total horizontal momentum before collision is equal to total horizontal momentum after collision. Total vertical momentum before collision is equal to total vertical momentum after collision. Yes. That's all. If you understand this, you can solve any problem. So apart from this, we have to fix the directions, plus and minus, everything. But this is a common theory. Hmm. Yeah. Is it clear now? Hmm. That's a, if you know this, you can answer any problem. But however, we'll solve the problem. Particularly this type of questions relevantly asked in paper 2, then paper 1. Okay. So we'll address those questions also. Yes, sir. Okay. Uh, so tomorrow evening, I will be recording solving on paper. Okay. So this paper. Yes, 20. 1 minute, sir. I'll check the paper. So I'll be recording for S25 QP 1 2 and S25 QP 2 2. Both papers I'll record tomorrow evening. Okay. If you want, you can join. Yeah, same link. Time alone, I'll let you know. Ah, ah, okay. In that case, we can do it by Saturday. No problem. Mm. Yeah, yeah. Yes, sir. Yes, sir. Like most probably we'll be recording like 9 o'clock or something. So you do not need to bother. Yeah, yeah. By the but okay. 1 minute, sir. Is it okay? Doubt clear? And any doubt? Yes, sir. Okay, 1 minute.